All right. Hello, everyone. Hi. Okay, I'll wait. Actually, I still need my slides anyways. The lab for this week has two questions. So the first question is working with image files a little bit and understanding pixels and stuff like that, and using the web page to convert between Ben and PNG. So the second question is to just go through the midterm and write answer code that actually compiles and runs correctly. So particularly, and it actually says in the question that if you got more than 75% on the midterm, you're free to go. Of course, it's still a good idea for you to, not from the lecture, from the lab. So of course, it's still a good idea to make sure that you make code that runs. If you got 75, then probably like most of your code probably would not run out of the box if you just typed it into the computer. But especially if you are under 75, like that, the only way to learn, like the lectures, they give you some context, but the only way to learn is to actually write code that works and to iterate until it works, right? So try again until it works. Yes.
Like just in the labs, but just on paper?
So the question was, would I recommend doing the labs on paper? And the answer is, I don't know. I think it might work for some people. It might be too much for other people. Well, yes, but like when you're training for a marathon, you don't always run marathons. You just run like a few, right? Mostly you're doing short runs. So it doesn't follow from the fact that on the exam you're writing on paper that the best thing to do to prepare is to exclusively write on paper. In fact, I would argue that it's more analogous to training for, I don't actually know how exactly people train for marathons, but I have actually run a half marathon in December, and that was the only time in my life that I had done that. And if I'm gonna, that's enough. So I did not train for the half marathon by running half marathons. In fact, I couldn't. And in fact, I stopped the first time that I managed to, and I haven't done it since. It wasn't actually a pleasant experience, particularly. So a little bit like ESC190 exams in that way, probably. But the serious point here is, I think the learning, at least kind of for me, it might be different, a little bit different, at least for different people. But for me, the learning happens when I write something, I see that, okay, like that did not go well, and I then fix it, and I say, okay, next time I won't do this. Either explicitly or just implicitly, my brain kind of figures out that that was a bad idea, and it would try to do something else. And I think so to me, at least intuitively, and I don't know that there are kind of studies about that. And even if there are studies about that, it wouldn't be uniform across different people. Different things might work for different people. But what I would suggest from my intuition is no, like write code mostly on the computer, because the computer can tell you whether you got it right or wrong, and it gives you an opportunity to fix it. I think in terms of like writing on paper, it's just that you don't want to be doing it the first time ever on the exam, but I think that's the extent of it. I think probably the midterm was like enough practice. The only exception I can think of is if someone, could get every question on the midterm pretty easily on the computer, but they were completely stuck on the midterm. And then I might say, okay, maybe you need to practice writing more in paper. At the same time, it might not be exactly a thing that you can practice, because I would say probably it's like the stress more than anything that would be interfering in this case, rather than just the medium on which you're writing. Again, might be wrong about that. But yeah, see what works. Certainly, if you get the time, I think for this course, for any other course, it makes sense to try to do a practice test, a practice exam, roughly in the same conditions as you would get on the actual exam. So like you're just sitting down for a few hours, you're not doing anything else, and you're just trying to do that exam. It might be that I think at this point you have practice with that general thing quite a lot from 1S and the midterms. But it might be subject specific, and it might be that you can go back and say, okay, like now I figured out how to do it. Right? It could be, I don't know. Okay, all right. So we'll do kind of some catch-up sessions online for people who want to kind of get a fresh start in 190 as well, because I feel like, and I was told that in other courses it happens as well, like it might very well be true that the people who are not in this room are making a rational decision right now, in that like they're so behind that they would not get much out of this lecture. Nobody's currently getting out much out of this lecture because I'm just babbling. So let me just start with the material. Okay. So what we were doing last time is thinking about how to implement the graph abstract data structure. And where we stop is we have two options. So to remind people, a graph is the thing on the left, right? So it's a bunch of nodes, or people say vertices, connected by edges, which can be directed or undirected. And we want to represent it on a computer somehow. And one way to do it is to say, okay, so we'll have a list of vertices or a list of nodes. So both vertex and node are used interchangeably. So I'm not going to pick one. And it could be a linked list as well. And then from each node, you have a linked list that stores the vertices to which the vertex is connected. So for example, 0 is connected to 5 and 2. And that is why 2 and 5 are in here in this linked list. I think after the lecture, someone asked me, like, should it be 2 and then 5, or should it be 5 and then 2? And the answer is it's implementation dependent. Here, I didn't say, and it could be arbitrary. You could, for example, say, I want to store them in a sorted order. If you store them in a sorted order, it's easier to find the vertex that you're looking for. So like if you want to know whether 0 is connected to 2, then, you know, like if you get, or like whether 0 is connected to 3, you get to 5, you know that 3 is not going to be there anyways, because 5 is already over 3. So retrieval can be a little bit faster. And on the other hand, insertion would be slower if you want to maintain the linked list as sorted. So there's trade-offs, and in this picture, at least, the order is kind of arbitrary, although it happens that they're all sorted here. So the other possibility that we discussed was an adjacency matrix. So what we have is we have whatever, in this case, 4 nodes labeled 0, 1, 2, 3. And this is an undirected graph. So what we'll do is inside of the corresponding entry to the possible connection. So for example, the connection between 0 and 1. So the connection between 0 and 1. The weight here is going to be 8. So because this is an undirected graph, the matrix is going to be symmetric, because the connection from 0 to 1 and the connection from 1 to 0, those are the same thing. So this is going to be equal to this is going to be equal to this, and so on. So by convention, especially in the weighted graph, what makes sense is if there is no edge between, for example, 0 and 2, that you would enter infinity in there. And you could imagine doing something different as well. So any kind of special symbol would work. It would be bad to, for example, say we had just had Pi Day. 3.14 would be the sign that there is no edge. Why is that bad? Yeah, so like there's no way to distinguish between a weight that's 3.14 and the 3.14 that indicates that there is no edge. Now, if you do 3.14159, whatever, like it's extremely unlikely that it would match, but it could happen. So infinity, of course, you could also say, well, maybe some weights are infinity. You could say that. The reason it kind of works is that if the weights indicate, for example, the costs of getting from location 3 to location 0 and vice versa, then infinity might as well not be connected because the cost to go through there is infinity. So you're not going to be using that edge, even though it technically exists, but its weight is infinity. So sometimes that works out, not in every application. So, okay. So like in particular, you could very well imagine that instead of this being the cost, it would be the other way. It would be like the negative cost. So what you get paid as an Uber driver to get from location 3 to 0. And then if you have like 0 to 1 is 0 to 2 is infinity, and that's what you get paid to go from 0 to 2, you probably will really want to drive there. So that would not work. In some contexts, it makes sense. Make sense? All right. So, okay. Let's kind of formally analyze the complexity of those operations. So kind of what's the cost there? So one kind of operation we might like to ask is there an edge between Vi and Vj? So the ith and the jth vertex. With the adjacency matrix, the complexity of that is O of 1, right? Because you just go to location ij in the adjacency matrix, and you see what the weight there is, right? So, is there a connection between 2 and 0? Well, no, because there is an infinity over here. And that's O of 1. You just need to figure out how to get to that location. That you can do using two additions and one multiplication, right? So that's the same as accessing a pixel in an image. You just do some math about how to get to that cell exactly, and you just go to that cell. Does that make sense? So that's O of 1. On the other hand, with the adjacency list, that would be O of D, where D is the maximum degree in the graph. So that's a little bit more complicated. So basically, we're thinking about, we have this adjacency list, right? And we want to know, is 0 connected to 5? Right? So how would we do it? Well, we would go through this list and we'll say, is this 5? Is this 5? And then if it is, then okay, there is a connection. On the other hand, if we want to ask, is 0 connected to 7? How many operations do we need? Anyone? So I want to know, using this kind of bunch of linked lists, whether 0 is connected to 7. Like, what's the complexity? Yeah. Yeah, so like depending on exactly, but something that's kind of like 2, right? So basically with, like, for example, 3. So what you're doing is you're saying, okay, like I'll go to this linked list and I need to go through the entire linked list in order to make sure that 7 is not there, because until I have gotten to the end of the list, I don't know, 7 might show up, right? So in the worst case, how many nodes do I need to go through? So there is a subtlety here, because you might naively say, well, if n is the number of nodes, it's got to be less than n nodes, because at worst, they need to go through every one of them. So here there is a more precise estimate, which is, if you look at the degree of the graph, if you remember, the degree is the maximum number of connections going out of any one node or going into any one node. Here it's the same because the connections are not directed. So the length of the linked list there, it's going to be at most D, where D is the degree, because the most nodes you can have in any one of the linked lists, like for example this guy or this guy, is the maximum number of nodes that are connected to any one node. Right? So at worst, you would have to go through D nodes in one of those linked lists. There's one more complication here. So if you remember, I said, well, like this vertical guy, it could also be a linked list. So why is that important? Yeah.
Since you get any node you can traverse.
Yeah, exactly. So if the 0, 1, 2, 3, 4, 5, 6, 7, 8 is also a linked list, so I just take all my nodes and I chain them up into a linked list because I decided that that's how I want to store them. Then yeah, like if I want to get to 8, I need to traverse, well, 7 and then I'll get to 8. So I need to basically do 8 times something operations. So how it's actually, so it might be sometimes that you want to do it as a linked list. However, if you have an array of nodes and then each node has a linked list connected to it, then it's OOP. So, and we saw this with the stacks and the queues already, where kind of the assumptions of exactly how what's stored and what exact information you have can be quite important. Yeah.
You just compared that we were just talking about connection, connection to
Whether there is a connection, yeah.
And then for the matrices, we're talking about an edge. That's a rather different thing. It's not.
No, I think you're asking about the path. So by connection, I do mean the edge. So I think by connection, you mean a path. So kind of like, can you get from 1 to 8 or something?
Yeah.
Yeah, that's a different question.
So we're comparing kind of different things here.
No, we're in both situations. We're asking, is there an edge or not? So here we're asking, is 0 connected to 5? And here as well, we're asking, is 3 connected to 0? By connected, I mean connected with an edge. So what you're asking about, is there a path that's coming? That's also a question you can ask, but that's not the question that we asked so far. Make sense? Yeah. How the two I do mean you mean the no, I think you mean this guy, right? So how two it does not. That's so 2 is connected to 6, and here there's only 6. Oh, so I understand the question now. So it's not that 2 is connected to 5. It's that for node 0, so for this guy, it's connected to both 2 and to 5. And this linked list stores the nodes to which 0 is connected. So 2 and 5 are not connected to each other. It's the content of the first node of this linked list is 2, and the content of the second one is 5. Okay. All right. So that's all of D, where D is the maximum degree in the graph. And again, assuming that you are storing the node, the kind of the linked lists that are associated with it, which each node as something like an array where you can access any of the linked lists within O(1). So let's say you want to find all the vertices that are adjacent to VI. So again, like thinking about nodes as airports, what are the airports to which you can get from YYZ or something, right? So in the adjacency matrix, what do you got to do in order to do this? Yeah, well, I know you know, someone else. You probably know too, someone else. All right, talk to your neighbor about how to find the adjacent vertices to V in this kind of structure. All right, so I guess you just didn't want to tell me, but you're okay telling your neighbor. Okay, fine. So yeah, so like what's connected to zero? Well, like you just gotta go and say, is zero connected to zero? Is one connect? And it could be. Sometimes there is self connections. Is one connected to zero? Is two connected to zero? Is three connected to zero? That's the only thing you could do. It's like just go through the entire row and ask like, is this a non-infinity or is this infinity? How long is it gonna take? Well, proportionate to the length of the row. What's the length of the row? That's the number of vertices, because each column, so like 0, 1, 2, 3, like those are all the vertices. How many columns, how many rows? Well, as many as there are vertices. So that's why that would be O of n, where n is the number of vertices in the graph. People often use kind of the absolute value. I think what you would know is, although you have done magnitude. So like this is kind of analogous to like the magnitude of a vector in linear algebra, which you also denote like this, maybe use 2 bars, I don't know. But like the norm, whatever. So that's where that comes from. So the size of B. What about the adjacency list? So we need to find all the vertices adjacent to 1. And one answer is, well, like you don't need to find them, they're right there. So if it happens that you want to return a linked list that contains all the nodes that are connected to 1, all you need to say is like return the linked list at 1. You don't even need to look at it. So you might argue, okay, that's not even O of D, that's like O of 1. If you want to do something with them, like you want to print them or you want to put them in a new data structure or something, then you have to go through each one of them. How many of them are there? Well, O of D, where D is the degree of the vertex about which you're asking. If you don't know which vertex you're going to be asking about, it's going to be O of D, where D is the largest possible degree in the graph. Make sense? So again, kind of all of this, and there's no way around it. All of this kind of has assumptions built in, like what exactly do you want to return? If you want to return a linked list, you're done. It's a one-liner that doesn't do anything. But like something like O of D, like basically what we're looking for is what are the trade-offs in terms of implementing the graph, right? And this is one of the trade-offs. So if you implement it as an adjacency matrix, then it's really easy to figure out if there is an edge between I and J. That's O of 1. With an adjacency list, that's not going to be the case. If you want to find all the vertices, again, like if it happens that your graph has a lot of nodes but very few edges, so that's what's called a sparse graph, then yeah, like you might like to do an adjacency list for those reasons, because if you often want to find all the vertices that are adjacent to VI, then you would be spending a lot of time just going through every possible vertex every time that you want to answer that question. So that's operations, and that's the trade-off there. The other The other trade-off is in terms of the space requirements, or as my slide would have it, requirements. This is how you know I did not use ChatGPT to make the slide. Like one strategy I think going forward would be you have to kind of insert typos intentionally, so that people don't think that you just generated whatever you said with ChatGPT. Of course, ChatGPT can generate typos if you asked it to. So once people are wise to that, it'll stop working. In my experience, however, it's not that people don't use ChatGPT. It's like they don't even run spell check, which is how I know that everyone has typos. Nor I, apparently. Okay. So adjacency matrix. We need to store n squared matrix entries where n is the number of vertices, right? Like that's the adjacency matrix. It's n by n, where n is the number of vertices. For the adjacency list, the analysis is a little bit more complicated. So let's look at the adjacency list again. So the question here is, how many nodes in total do we have? And we have two kinds of things here, right? So we have nodes in the linked list, and we have this linked list, or probably this array, right? So like what you store the 0, the 1, the 2, and the 3 in, right? So how many nodes in general in the linked list as a whole are there? So literally how many on the slide? I would say 6. Yeah, but by the way, and I'll stop bobbling. And so like an important update about the Bulgarian head shaking, which is completely true. I was also told, which I did not know, that in India, especially in South India, it's a whole other thing where head shaking can mean basically anything. So you can go on YouTube and see. Okay. So I'm not. I did watch like about 10 minutes of that. I'm not going to try to reproduce it, but yeah. Okay. So 6 nodes. 6 nodes over here, and the reason there is 6 is because we have a connection between 0 and 1, and a connection between 1 and 0, and then a connection between 0 and 3, and a connection between 3 and 0. So basically, for every connection, we have 2 nodes in there. So one that's a node in, for example, for 0 and 3, one that's in this list, so 0, 3, and one that's in this list, 3, 0. So that means we have twice as many nodes as we have edges in all of the linked lists taken together. Right? So this is a trick that we've seen several times before. If you try to analyze it like linked list by linked list, it's going to be kind of difficult, and you'd have to overestimate basically. But you can ask, well, how many nodes in total are there in the linked list? And the answer is, well, twice as many as there are edges, because each edge, like 0 to 3, corresponds to this 6 and then this 6, and there is always 2 of them if it's an undirected graph, right? Yeah.
Why are we counting the number?
We want to know how much space we're going to take up
In our linked list representation.
In the whole thing.
But is it wrong to say that there are 4 nodes there? Nodes is like vertices. That's what
it's not wrong to say that there are 4 nodes, but we're taking more space than that.
So like say it takes like 6.
Well, it takes sorry. So by nodes, I mean those guys.
Oh, linked list nodes.
Yes. Yes. Yeah.
So I'm
spot says the space requirement for these is number of vertices.
Yeah, we're getting to that. Yeah, so far we counted the number of nodes in the linked lists. So, and there is twice as many of them as there are edges. So a number that's proportionate to edges. However, we also have this guy. So it might be that there are no edges at all in the graph, and you still have to store a null here, a null here, a null here, and a null here. So this array, how much would that take up? Well, proportional to the number of nodes. Right? So this would be 4 for the 4 nodes in the graph, plus 2 times 3, where 3 is the number of edges.
And that's if you're storing it as linked list or
Either way, actually. Yeah.
on that things like just a block and then you don't need to store anything at
Well, what's the size of the block?
so you can store that, I guess.
No, like you store, like if you're storing it as a block, meaning like an array, well, you got to reserve space in the array. It might change from now to something else later. Right? So we'll have time to implement it today as well. So we'll see it that way. Does that make sense to everyone? Does anyone else want to argue? No, that was a good question. Okay. So what we're saying is in order to store this graph over here, so we need twice the number of edges to store those guys. And we're using the trick of saying in the aggregate, how many nodes are there in the linked list overall. And then we need to store this array, which has a number of elements that's proportional to the number of nodes because it's equal to the number of nodes. So that means that the space requirement is something like, whatever constant times the number of vertices plus another constant times the number of edges. And that's O of V plus E. So I think most people would think of this as we're just dropping the constants. Let's just do a quick proof here. So A1 times V plus A2 times E is smaller than equal to max A1, A2. V plus E, and this really is a multiplicative constant that you could just drop. Make sense? So this can make quite a bit of a difference, right? So if you imagine, if you imagine something like Google's data set of all the web pages and which web pages link to which other web pages, right? So there are, probably hundreds of millions of web pages indexed, which means that if you happen to choose to store it as an adjacency matrix, it would be 100 million squared, which is a lot. Which is not to say that Google uses linked lists. I don't actually know what exactly they're. I don't think they're using either actually. But here the size would just grow linearly with the number of nodes, so the number of web pages, and the number of edges, so like the number of links between the different web pages. All right. So yes.
So I guess we're not taking into account. We did talk about like sparse matrices before. And
yeah.
what you're supposed to store them. Is this assuming This is assuming you're not using like some nice way to sort of just really storing all these zeros everywhere.
Yeah, well, I mean, like, yeah, so the question was like, like, aren't there like better ways to store sparse matrices than just literally as a matrix? And the answer is, well, yes. For example, you can use a bunch of linked lists.
Or like we did last year.
Yeah. Or you can do something like a hash table. So if you do something like what we had done last year, your problem would be that you have to go through all the edges in order to figure out whether anything is connected. So that would be very slow. So right. So there's different, yeah. And again, kind of with a hash table, actually you can do something better than in the average case. You can do something better than just go through all of them. In the worst case, no. And again, actually underneath a dictionary would be a bunch of linked lists as it happens. So yeah, but that's a good point. All right. Okay. So let's try to implement a graph. So a graph is kind of like a linked list, right? A linked list, in fact, is a kind of a graph. So it's gonna look pretty similar. So I'm not gonna do either of the options on the slides. I'm gonna do something different, and then we're gonna analyze that. So I'm gonna define a class node. And what I'm going to do here is I'm just going to have like some kind of value that's stored in each node. It could be a string, or it could be a number, or like anything that you want.
Are we by node, do we like a linked list node, or are we talking about a graph vertex?
Actually, I could be doing both, but I do mean a graph vertex. I could use the same class for both, actually, if I really wanted. I mean, if it's like clearer to you, just for you, we'll do it, but that's like not the usual thing. So I mean, it is just a name. However, like, it's okay. I changed my mind. We're saying node. Sorry. How about in your mind, just rename the nodes in the linked list to vertices? That would be, yeah. So okay. So that would be node, and so it is just a name. However, I'm trying to kind of write things the way people usually do, which I understand was your objection in the first place, but I'm gonna try to stick to convention here. So we'll have a value, and now what I'm gonna do is I'm gonna store the nodes that are connected to this node in a list called children. So that's kind of the usual terminology here that people sometimes use. So people can also say neighbors. In fact, I will say neighbors. But the idea would be that in a directed graph, you can kind of like look at it as if it were like a family tree, I suppose, right? Where like 5 has begotten 7, and 7 has begotten 8, and so on, okay? So 7 would be 5's child, and 5 would be 7's parent. Let's make it less personal and call them neighbors with a U. So okay. So that's the node. So now we want to create a graph, right? So what I need to do here is I need to make just a bunch of nodes. And then I'll connect them. So I'll create YYZ. What's LHR? Never heard of that. YVR. And let's, is that Calgary? Okay, we had enough like large cities. So let's do like, what's the name of the Whitehorse Airport? Maybe Copilot knows. Copilot does not. Is there one in one? It should be. Okay, we'll just name it Whitehorse. Okay. So now we'll hook them up. So I'll say, okay, so the neighbors of YYZ, that's going to be a list. And I can just say, okay, so YYZ is neighbors with Vancouver and with Montreal, but not with Whitehorse. And then Vancouver definitely has YYZ, so I'm assuming that it's symmetric. And it's neighbors with Montreal, and it's also neighbors with Whitehorse. And then Montreal is just neighbors with Toronto. Yeah, I don't know if everyone knows those things. So this is so in Canada, for weird historical reasons, all the airports call signs start with Y. I believe it has to do with like radio call signs or something. So this would be Toronto, this is Montreal, and this is Vancouver, and then Copilot did not know the call sign for Whitehorse. Yeah.
So we're creating a directed graph.
So here what we're doing is we're creating what's in effect not a directed graph, because I'm making sure that if YYZ is neighbors with YVR, then YVR is also neighbors with YYZ, but I'm doing it manually, right? So it could be, and so far I haven't said what Whitehorse is, but if I say it like this, then this can be interpreted as a non-directed graph because I recorded each edge twice. There is not really a good way to not, in this representation, to not record each edge twice. You could do that, but then at lookup time, you would have to not just look at the neighbors of YYZ, you would also need to look at whether any of the other nodes are neighbors with YYZ in their list, and that would take a long time. So with the list representation, that's kind of the best you can do, is you will have some redundancy. With an adjacency matrix representation, it's not really like that, right? So like nothing, so like if you know that it's not, if you know that the graph is definitely not directed, you could just store the upper triangle. And just like, you know, like if you want to look up YJ where IJ where I is, I guess, smaller than J, then you just look up JI instead.
That's like the feature of the list that we have to manually go and
again, like not exactly have to, you could get away with, like if the information is there, you could find it in principle. It's just that if you don't make sure that there is a redundancy, then the complexity goes way up, because you have to not just look at the list of the neighbors of YYZ in order to know what's connected to YYZ. You'd have to look at all the other nodes to see if their one of their neighbors is YYZ. All right. So, okay. So that is it. So that is the graph, right? So because the graph is not like linear, like a linked list, you kind of just have like one head. So what you could, because there could be, you know, multiple different clusters of airports that are connected to each other, but are not connected between each other. So there could not be like one airport where you start. if you do have multiple components in the graph, you could in principle store like one representative of each component. People sometimes do that. But in general, like that's the graph. All right. So in Python, it's kind of really straightforward because all you need to do, like all the choices that you have are like, if you want to set the neighbors as like, if YYZ is neighbors with YVR, you would say YVR here. So in C, you could think of neighbors as, and we'll do it next time as well, as an array of pointers. And then if you store YVR as a pointer, you could again do it like this. Okay. So what's the complexity of YYZ? Well, that's the same as what we discussed, right? So you have to go to YYZ neighbors and look through every element to see if it happens to be equal to YVR. So that's SOAP-D. One minute left. I have one last question. So in what situation is the, in terms of complexity of operations, what operation would take longer here than if you had linked lists? So let's go back. So like, what operation is fast with linked lists, but not fast with ordinary lists? Yeah. Insert, that's right. And here it's the same. So if you like made a new connection between two cities and wanted to enter it into the graph, then you would have to append to the neighbors. And if you remember, appending to a list can be all of that, because it might be that you need to copy the entire list to a new location where there is enough space. So for that reason, if you want to insert, then you probably want linked lists rather than just array lists. That is more annoying to implement. All right. Again, I really encourage you to do the first questions on the midterm. Make sure that you can compile them and run them. You don't really know that you know this stuff until you've made it actually work. So yeah. All right. See ya. Bye. Thanks.
I'm sorry. I'm still.